Hello everyone, I'm Joey, and today I'll be giving the lecture for the F equals MA Club online lecture day 5. So this week we talked about circular motion and rotation. Alright, so just a little bit of review. Last time we talked about momentum, impulse, and collisions. So for momentum, remember we have the conservation of momentum. Impulse, that's going to be our change of momentum, and that's also going to be equal to F dt. And we also have our collisions, which are, we talked about two types of collisions. We have elastic and inelastic, right? All right, so let's first talk about circular motion, okay? So remember we have our translational and rotational analogs, right? So we have position, velocity, acceleration, and we have our angular position denoted as theta. We have our angular velocity denoted as omega, and we have our angular acceleration denoted as alpha, right? Okay, so remember that we can convert between the two by having our radius in our equation. So our position would be equal to our angular position times r. Our velocity would be our omega times r, and so on and so forth. Remember that our kinematic equations also translate between both. And we also have our other analogs such as mass, which becomes our moment of inertia, which is how easily something can be rotated. We have Newton's second law, which is F equals ma, which translates to our torque equaling our inertia times our angular acceleration. And the rest of these we might talk a little bit more in the future, but it's just nice to have down kind of in your mind. All right. Remember that our total acceleration is going to be the sum of our radial and tangential acceleration in uniform circular motion. And that's going to be in the form of this when I mean sum, which is going to be our radial acceleration squared plus our tangential acceleration squared. And the square root of all that is going to be equal to our total acceleration, right? And here in this picture, we can see what I mean by radial and tangential acceleration, right? So this isn't a bonus question. I just forgot to leave out this slide. But for anyone who was actually at the lesson, I gave the wrong worksheet out. So I would recommend you guys do this problem instead of the last problem on that. And I'll cover the other problem that I'm going to omit probably next week because that's actually going to be relevant there. Alright, so now we go on to rotation, right? So we have torque and force, where our torque, I don't know why it's denoted like that now. It's supposed to be a tau, which looks like that. That's not clear. It's going to look something like this, where it's like that and then there. And I'll write it down later. But that's going to be equal to our force times our r sine theta, or r cross product f, which is something that you only do in C. But yeah, we also have our torque is equal to our moment of inertia times our angular acceleration, as said before, and our torque can be expressed as basically force and rotation, right? So moment of inertia, we're going to talk about this a little bit more next time, but some of the problems in our worksheet are going to have a little bit of this stuff, so it's just good to memorize these formulas, or at least have a general idea of what they are, okay? So for translation and rotation, we can utilize Newton's second law for two uses. First is the translation of our center of mass, which we're going to use F equals ma. And for the rotation of our center of mass around a fixed point, that's going to give us our torque is equal to our moment of inertia times our angular acceleration. So for a rigid object, it'll have the same omega, same angular velocity throughout. So our moment of inertia can be formularized as shown before, right? Remember that torque equals IA is only I alpha is only valid if the origin is at a fixed point or the center of mass, or both. You must choose the same origin for your torque and your moment of inertia. And whenever your motion changes, for translations you must use forces, and for rotations you must use torques, right? Okay, let's move on to our worksheet, right? So let's look at our first problem then. First problem, what is this? A radio-controlled car is attached at a stake in the ground by a 3-meter long piece of string, forced to move in a circular path. Car has an angular velocity, initial angular velocity of 1 rad per second, 1 radian per second, and it smoothly accelerates at a rate of 4 radians per second squared. The string will break when the centripetal acceleration exceeds 243 meters per second squared. How long can the car accelerate at this rate before the string breaks, right? Okay, let's switch to our scene here. So we have okay, this is going to be a little bit rough. That's not right. Okay, so we have a stake in the ground, right? This is our stake in the ground, and we also have a string that's tying a car. Let's just draw a car here, a radio-controlled car, right? Doesn't matter. Let's just denote this as a block, right? And we have a few wheels or something like that. I don't care. So we have a block. We know that this radius is what is this radius? 3 meters, right? So 3 meters. Our car has an initial angular velocity of, what is that, 1 radian per second, right? And it has an angular acceleration, a constant angular acceleration of 4 radians per second squared, right? We know that the string will break if our centripetal acceleration is equal to 243 meters per second squared, right? All right, we can start, and we just need to find the time. So let's start working on this, right? Our centripetal acceleration is going to be equal to our v squared over r, or is equal to our omega squared times r, right? And I forgot to cover this, but this is probably going to be a very important formula, right? So we really shouldn't use this one, and we should instead use this one, right? Because we already have angular and angular acceleration and velocity, we should just stick with this, right? So let's set these, let's add these values in, right? So we have at 243 meters per second squared, the string is going to break. So let's find the angular velocity at that point. So we have 243 equals 3 omega f, our final angular velocity squared, right? So that means that our final velocity is going to be equal to the square root of 243 divided by 3, right? This is going to be the square root of 81, which is going to give our final omega 9. Per second, right? Okay, so moving on from here, we have our final angular velocity, we have our initial angular velocity, we have an angular acceleration, and we're trying to find our time, right? So we can look back at some of our rotational analogs for our kinematic equations and find that our final velocity is going to be equal to our initial velocity plus our angular acceleration times time, right? Let's just plug these values in. So 9 equals 1 plus 4t. T is then equal to 8 divided by 4, which is 2 seconds. And if we look back at our little at our worksheet, that'll give us answer choice E, right? Over there. All right, next one. There is a ring outside of Saturn. In order to distinguish if the ring is actually part of Saturn or instead part of the satellites of Saturn, we need to know the relation between the velocity v of each layer in the ring and the distance r of the layer to the center of Saturn. Which of the following statements is correct? All right, so just first off, that symbol means directly proportional to. So I know that. This is actually fairly simple. Let's just get straight into it. So we have our v. We can just use this equation. Please work with me. V is equal to our omega times r, right? That's basically all we need. So that means that our v is directly proportional to our r, right? Because we need to know, because this is an object within Saturn, right? It's an object within Saturn, and something like that, right? Oh no. So something like that, right? If an object is in Saturn, it's going to have the same angular velocity as Saturn. As said before, a rigid object will always have the same omega throughout. So that means that any object that's inside Saturn is going to have the same angular velocity. So given that, we can use this equation, and that means that our v is directly proportional to our r. So if we look back at our answer choices here, we'll see that our answer will be A, where if v is directly proportional to r, then the layer is part of Saturn. And the rest of these, you can just double check them. Yeah. And if we wanted to solve for any object that's on part of the satellites of the Saturn, I'm pretty sure we have to use gravitation. And since we don't know gravitation yet, that's going to be saved for later. Alright? So, next, a uniform. Oh my god, I need to stop scrolling. Next, a uniform disk is being pulled by a force F through a string attached to its center of mass. Assume that the disk is rolling smoothly without slipping, right? What does this ask us? At a certain instant of time, in which region of the disk, if any, is there a point moving with zero total acceleration? So, at the class, a lot of people said that, answered E almost immediately, saying that, oh, the entire circle must have non-zero acceleration. This is not entirely true, and we can see that in a little diagram that I'm going to draw right now, right? So we have our circle, we also have our little line right here, or something like that, a floating circle, close enough, right? So, we have a circle, we have a force that's pulling, the circle in this direction, right? It's rolling, which means that it has a radial acceleration and a tangential acceleration, right? We have 4 quadrants, I think. So we have 4 quadrants. Something like that, right? We have 1, I think I remember these, 3, and 4, right? These are our 4 quadrants. So let's choose a point on each one of these quadrants, right? So let's choose this point here, this point here, this point here, this point here. And let's go in order of all these quadrants, right? Our radial acceleration is going to be pointing in this direction. Our tangential acceleration is going to be pointing in this direction. And our force is going to have an acceleration in this direction, right? So the final sum of these is not going to be 0. It's going to be probably pointing in this direction, right? Next, let's go for quadrant 2. Our radial acceleration is here. Our tangential acceleration is here. And our acceleration caused by this is going to be here. So in the end, this is also not going to be 0. It's going to probably be in that direction, right? Next, we have our quadrant 3, where our radial acceleration is here. Our tangential acceleration is here, and our force is here, right? So that's also non-zero. And here's where the interesting part happens, right? For quadrant 4, our radial acceleration is in this direction. Tangential acceleration is in this direction. And our force is in this direction, right? This means that at this point, there's some point on quadrant 4 where all the forces, where all the accelerations can technically cancel out. So if we look back at our little worksheet, we can see that that's going to give us D, which is region 4. And this is slightly confusing. You might think that the entire circle might have uniform acceleration. However, since we have a force and we also have everything going on, there is a possible point where all these can cancel, right? Okay. That was not intentional. Okay. So, next problem, right? So, a hollow cylinder with a very thin wall and a block are placed at rest at the top of a plane. I can't speak today. With inclination theta above the horizontal. Cylinder rolls down the plane without slipping. That's a big thing. Block slides down the plane. It's found that both objects reach the bottom of the plane simultaneously. What is the coefficient of kinetic friction between the block and the plane? This is actually a very tricky problem. Let's start going through it then. So, we have a plane, right? We have an inclined plane, right? We have an inclined plane. Let's just say it's like that. And then we have that, right? We have a plane. Let's say it's very long. This is inspired by a certain student that I had to teach who drew a very long plane. So, on one of these, we have a cylinder, right? A very hollow cylinder. And we also have a block on another. Start from the same place, same inclination, and they both reach the bottom at the same time, right? So first things first, let's solve for the cylinder, because that's probably going to be the harder one, right? So we know that for both of these, we're going to have some force, for both of these, we're going to have some force that's pulling it down, and some frictional force pulling it back. So the interesting thing about the cylinder, right? If it's rolling without slipping, that means that there's already friction being generated to make it not slip. Or else, if there were no friction, then this would just slip in place and just not work. Well, like if it were flat, it would just probably slide down, right? So let's work on the circle first. We know that our torque is going to be equal to our moment of inertia times our angular acceleration, right? Our torque, in this case, is going to be equal to our force times our radius, right? And we're talking about the frictional force, so that's going to be our force, frictional force, times our radius. It's going to be equal to mr squared, because that's the moment of inertia of a hollow hoop or a tube or something like that. Mr squared. This is going to be mr squared times our angular acceleration, which is going to be a over r, right? So after a bit of canceling, we can determine that our frictional force is just going to be equal to ma, right? All right, let's just select all of this. Move this over. Oh shoot, there's the other stuff as well. Alright, I'm gonna move this up and then erase some of the bottom stuff, right? Okay, so let's first erase. While I erase, the big thing that we need to remember now is that we need to find the net force and the net acceleration, right? So let's calculate the net forces for the cylinder, right? So we have what two forces are acting on it? The one pulling it down and the frictional force that's slowing it down, right? So we have the force pulling it down the ramp, which is going to be mg sine theta, minus our frictional force, right? Going to give us ma, right? This is our net mass, and this is our net acceleration. This is going to be equal to mg sine theta minus ma. It's going to give us ma. Cross out all the mass. G sine of theta is equal to 2a. So we can say that our acceleration is going to be g sine of theta over 2, right? Okay, now let's move on to the block, right? Our block is going to have two forces. We know g sine of theta, mg sine theta, and mu mg cosine theta, which is going to be our frictional coefficient, right? So let's first let's just pretend everything's fine, right? Let's just write up here. So we have our mg sine theta, right, for the block, minus mu mg cosine theta. It's going to give us mass times acceleration, right? Let's first eliminate all these m's, and we know that our acceleration is here, because these two must have the same acceleration to both reach the bottom of the ramp at the same time. So let's substitute in, so g sine of theta minus mu g cosine theta is going to actually give us g sine of theta over 2. Now if we move this over here and move this over here, that gives us mu g cosine theta is going to give us g sine of theta over 2. Since this minus this is going to give us this, right? That means that our mu, we can, mu, we can cancel off our g's. Sine divided by cosine is tangent. So, that's going to give us 1 over 2 tangent theta, right? That's how you solve this problem. It's very convoluted, but this is going to be one of the harder units. So, yeah. Let's go back. And if we look, that's going to give us option C, I believe. All right. Let's move on to the next one. This is also very tricky, so don't be too intimidated. Sorry, I'm having some technical difficulties. All right. Let's start then. So, a crew of scientists build a new space station shaped like a wheel of radius r with all the mass at the rim. When the crew arrives, the station will be set, rotating at a rate, radial acceleration of g, simulating Earth's surface gravity. I'll classify 2 rockets, each with t newtons, mounted on the station's rim. So how long, a time t, does one need to fire the rockets to achieve the desired condition, right? Alright, let's start doing this then. So we have a station, right? We have a station. Why is it working? Stop. No. Okay, so we have a station, right? We have a station with radius of r, all the mass, mass m around the rim, right? Which makes this basically a hoop. And we also have two rockets, each providing a force of t, right? So t and t. And at that point, it'll simulate radial acceleration of g, right? So that means that our angular acceleration is going to be equal to g, right? Yeah, that's what it's trying to implement. And so, with this, we can say that our a divided by r equals g, right? Which means that our acceleration is going to be equal to gr. Right? Sorry, I'm having some issues with this thing. Just give me one moment. Please work with me. Sorry for the wait. I don't know why it's just not responding to me. Okay. It's working again. Alright. So, let's try this again, right? So our centripetal acceleration is going to be equal to g, not our angular acceleration, my bad. Our centripetal acceleration is going to be equal to g, which means that our omega squared times r is going to be equal to g. Omega is then equal to the square root of g over r, right? So that's our angular speed given to us. That means that our rockets need to provide a certain acceleration, right? So we can first derive torque equals moment of inertia times our angular acceleration. Torque is then equal to 2t times r, since we have two rockets providing force t. So 2t times r is going to be equal to, this is a hoop, so I equals mr squared. That's going to be mr squared times a, right? From there, we can say that our acceleration is then equal to 2tr over mr squared, right? Which means we can cancel these, and that's our angular acceleration, right? That means our time, we have our equation, which is our angular speed is going to be, angular velocity is going to be equal to our angular acceleration times time. So that means our time is going to be equal to our angular speed over our angular acceleration, which is going to give us, what is this, square root of g over r times, divided by 2t times mr, right? Because it's multiplying by reciprocal. Which means that our t, sorry for writing all over the place, but that means our t, if we move our r straight into there, that means our t is going to be equal to the square root of gr times m divided by 2t. Right? And if we look back at our slideshow, that's going to give us b. Alright. Now that that's finished, it's time to work on one of the harder problems. So, this is the one that was just in the slideshow. A small bead is placed on top of a frictionless glass sphere of diameter d, which is very interesting. They typically don't use that. As shown, the bead is given a slight push and starts sliding down the sphere. Find the speed v of the bead at the point at which the bead leaves the sphere. Right? Okay, so this is actually going to use quite a lot of equations. Our first one is probably going to be conservation of energy, right? We have a certain height, and then at once it reaches 0 relative to that certain height, that's when the bead will fall off, right? So we can say that our mgh is going to be equal to 1 over 2 mv squared. And there's where we get our v. Now, dumb, stupid me thought, oh yeah, h is just going to be d, so we can just substitute that, and we can get a or some other number. And then I realized that I was a big boy idiot. So, it's not just that, because our h is not going to be our entire diameter, but at this height, where 0 is going to be at the point where it falls off, and h is going to be from there to the top of to the original starting place of the bead. Okay? So, the next part is going to be to find where exactly that falls, right? So that's going to fall at around here, right? Where our h is going to be equal to r times 1 minus cosine of theta. And we can find that it's kind of similar to pendulums, which we'll talk about later, where this is our entire r, right? This is our r. This is our r cosine theta. Here, right? This is our r cosine theta, where this is our cosine. Yeah, where that's our cosine. And we can say that this is also r. So this is r cosine theta. So we can say that this h is going to be r times 1 minus cosine theta, because it's r minus r cosine theta. Okay, moving on from here. Now we just need to find what cosine theta is. And that's actually going to be quite tricky. But that's going to use just one more little element, which is going to prove very interesting for us. Right? Please work. No, work with me. Oh, no. Okay, just give me a moment. Why is it always like this? Work. Sorry for all the delays. It's gonna take a little bit. I don't know why. Is it working now? Okay, so the final equation is going to be kind of close to this, right? Where the point at which it falls off, we first have two forces acting on. We have two forces technically acting on this, right? We have our gravitational force, and we have our centripetal force, right? So that means that we can split our gravitational force back into two elements, right? We have our mg sine theta, and we also have our normal force, right? So we also have another force in this direction, but we can say that our normal force is here. And we also have a centripetal acceleration here. So this is going to be mg cosine theta, right? And this is going to be equal to mv squared over r, right? Because our centripetal acceleration is v squared over r, so our centripetal force is going to be F equals ma, which is mv squared over r. So now we know that at the point that it falls off, or at the point that it loses contact, mg cosine of theta is going to have to equal to mv squared over r, right? That means that our cosine of theta is going to be equal to v squared over gr. So now we can plug that back into here and plug that back into here. So that means our mgr minus mg v squared over gr is going to be equal to 1 over 2 mv squared. Hopefully I got that right. If I didn't, I will be very embarrassed. So let's start crossing stuff out. So here, 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 we have these two can cross out. That means that our gr minus v squared over r is equal to 1 over 2 v squared. Right? And let me double check the validity of that. That is wrong. That is very wrong. I am very sorry. So there should be another r here, just because of this, right? It's mgr times v squared over gr. So these cross out, these two cross out, and all the m's can cross out as well, right? That gives us gr minus v squared is equal to 1 over 2 v squared. If we move this over here, that means that 3 over 2 v squared is equal to gr, which means that v squared is going to be equal to the square root of 2gr over 3. This made me almost circle C until I realized that they were asking for diameter, right? And our diameter is going to be equal to 2 times our radius, which means that our final answer, sorry, that's not supposed to be squared, v is going to be the square root of g times our diameter over 3. Alright, that's it. Sorry for all the pauses. The credit just doesn't work well with OBS, but that's about it. Alright, thank you so much for attending, and I'll see you next week. See you then.